In a previous video, we talked about how the derivative of a function is in itself a function. So anything we can do to the initial function, we can do to the derivative, which means we can continue to take derivatives of derivatives. If I start with a function f of x and I take its derivative, I get f prime of x. But we've just said that that is in itself a function, which means I can take the derivative of f prime of x. And so we can write that a few different ways. We can use that kind of functional notation where we're actually taking taking a derivative on a function. But what that means that we get to the second derivative, and we can indicate that a few different ways. We can indicate that with the f double prime of x. We can take the derivative of that yet again, and that would get us to the third derivative, which we can indicate with 3 primes on our f of x. But we can see that this is very quickly going to get quite cumbersome because let's say I want to take 15 derivatives, right? Typically we don't go that far, but there are reasons we want to go past the first derivative, and we're going to talk a little bit about that in this video. But let's say we did. Let's say we wanted to go out 15 derivatives. I don't want to have to write 15 primes there or write this every single time. So what we can do too is we can represent the derivative by putting what looks to be an exponent on that function, but I'm going to put it in parentheses. So f in parentheses 2x or f3x. What that is indicating is the derivative that I'm taking. So if I write f15 of x, then that's indicating that that is the 15th derivative. Now remember, there are other ways we can write these. So we write this if the graph y is representing the function of f of x, we could write it dy over dx. And so we could write this as d2y over dx. And so we can continue doing this as many times as we would like. And so again, here we'd have d 3y dx to the third, indicating the third derivative of our y. We could use the function name itself, so d3, sorry, that should be a 2, because it's only the second derivative, but d2 of f over dx squared. So, depending on if we're looking at the graph, we will use the y's to represent the equation of a graph. The function we call the f. So lots of different ways we can write it. But let's just work on taking a couple of derivatives. So let's just find a function, f of x is equal to 8x cubed minus 2x squared plus 11x minus 8. So I have quite a large function because if I'm going to take derivatives, we're going to use our shortcut rules on these, or our rules of finding derivatives, the power rules along with our sum difference rules. But we know each time we use the power rule, that power goes down by 1. So if I start at just a linear equation, it's going to go to 0 pretty quickly. So let's say we wanted to find the first derivative. We'd have 3 times 8, which is 24. And then the x is now going to be squared minus 4x plus 11. The 8, of course, goes to 0. We could take the second derivative, 48x minus 4. The third derivative, 48. Usually by the time you get to the fourth derivative, you switch to that alternative in parentheses notation. It's merely just a factor of not wanting to write a whole lot. So figure you write 1 symbol, 2 symbols is a lot easier than writing 3 different symbols. By the time you hit 4, you're writing 3 symbols again. So just kind of honestly out of laziness, but it's standard notational math notation to use the apostrophes until you get to the fourth, and then you kind of switch over. You can switch over before that. But we see by the time we get to that fourth derivative, we get to 0, and that's going to continue to stay 0. And if we think about why that would be, let's kind of take a little sidebar on this. Let's start with the linear function. Well, we know linear functions have a constant rate of change. And so if I name this my function f of x, right, whatever the actual equation is, we find that derivative. It looks to be approximately 1, maybe a little bit under, but I'm not going to really label it very exactly. But it is a constant slope. And so when we go to take that derivative, our slope turns into just a horizontal line. By the time we go to take the next derivative, because it's a horizontal line, our slope is 0. So our second derivative goes to 0. So with these polynomial functions, they all will go to 0. If I were to start with a cubic, Well, if we're to look at that and find its derivative, I'll call this point A and I'll call this point B. I'm not going to assign the y values. If I see at point A, the slope is 0. I see at point B, the slope is 0. Before that, the slope was positive, but it is getting closer and closer to 0 as it comes in. Then it goes negative for a while, but it's speeding up until a certain point and then it's slowing back down. And then we can see once it hits B, it turns back to a positive slope, and so it starts going back up again. And notice the shape that we just drew for our first derivative, rather. It's a quadratic. So the derivative of a cubic is a quadratic. That's the idea of reducing the exponent by 1. We went from a degree 3 to a degree 2 polynomial. Well, let's take that and find its derivative. So this is the second derivative of f. And so now we can see that the point at which it's 0 is somewhere right in here. Again, I haven't done these super precise to where, I know exactly. It's just kind of rough ballpark sketch. But we can see that, right around in here, it turns right off the axis. And we can see that lowest point right in here is also the turning point, meaning its derivative 0. If we were to its left, it's a negative decreasing slope, and it's getting closer and closer to 0. And then once we hit that 0, it becomes a positive slope and it goes up from there. And notice what equation we've just drawn. We've drawn a line again. So then what we saw just a second ago is if I were to take its derivative, we can see its positive slope. And so if I were to graph the derivative of this, it's just a horizontal line, approximately maybe around 1. We don't have the exact value, so we don't know. And then if we're to take the derivative of that, well, now we know it's exactly 0. So it's always very easy to see where the zeros are, because anytime we have a slope that is constant, for instance, the constant line, or in here, or here, and here, the constant slopes just have a slope of 0. So all polynomials will end up at that horizontal line, and that's why we don't tend to see that we have huge derivatives. They just tend to peter out. That's not every function. Trig functions will never go to 0. Sine goes to cosine, back to sine. Now the signs, positive, negative signs on that switch, they continue to go back and forth because think about the sine cosine graph. It is kind of always on the move, except for a few spots. It is always on the move, and so it's always going to just keep having other trig values as its own derivative. The square root function, the exponential function, lots of other functions won't peter out, but still it just tends to be that we don't have a use for really, really high derivatives. Now we can go a few in. Now a great example of these higher order derivatives revolves around position, and we're going to work with these problems in this course. But position, if we define this as the s of t function, a lot of times for position we use this s of t to represent position based on time. If we were to take the derivative of the position function based on time, s prime t, what that actually gives us is velocity. And that should make sense. If I'm looking at how a car is traveling down the road, and I look at an instant in time and I want to know what its rate of change is, we define rate of change as speed, or to be a little more precise, velocity, because velocity builds in whether it's going forward or backward. What if I take the derivative of velocity, or the second derivative of position? So this would be the, and velocity we tend to label with v of t. Second derivative of position, which is the derivative of velocity, that actually gives us acceleration. And that should make sense too, because if we look at how velocity is changing, how quickly or slowly is our speed changing, well, that depends on, are we accelerating, are we decelerating, are we pressing the gas pedal, or are we pressing the brake, or we could be staying the same. And we can continue to take derivatives in the same fashion. So if I look at the third derivative of position, which is the second derivative of velocity, which I forgot to define acceleration. Acceleration is a of t. Would be the derivative of acceleration. Use that. That gives us something called jerk. And this one we probably don't hear of a whole lot. We don't hear this used in everyday words, but it kind of makes sense, because if you think about slamming down on that brake pedal, where are you going to get? What's going to happen to your body? You're going to be jerked forward, or if you're slamming the gas pedal, you're going to get jerked backwards. Kind of think of those G-forces on roller coasters, things like that. Now, jerk doesn't get its own lettering, at least not a common one that I'm aware of. But we can continue to kind of use the same idea of derivatives, and let me switch over to the fourth because I was getting a little cumbersome. The fourth derivative position, which is the third derivative of velocity, which is the second derivative of acceleration, which is the first derivative of jerk, is something called jounce. And where I think most of you probably hadn't heard of jerk, even less probably have heard of jounce. Jounce does kind of get, there's a kind of a playful side of math too, believe it or not. Also gets called snap sometimes. And that launches into a fun sequence where the derivative of jounce is called crackle. And then the derivative of crackle is pop, snap, crackle, pop. And then I've also heard an even more fun lock and drop, but these aren't as nearly as officially named as the others. You wouldn't typically see these in a textbook, but if you look at kind of some mathematical papers, we have to have a way of referring to these things. We might as well make it a little bit fun. So you know, when you're creating things in math, or when you're doing things in math and writing formal papers, you get kind of make up things as you see fit. And so those were some of the names that have been used in formal writings before. But again, I think for most of engineers and the mainstream or more common, I guess, positions we would see in everyday society, we don't tend to go a whole lot past jounce. Now, if you're a rocket scientist or a theoretical physicist, you're probably getting into some of the further ones. And then, of course, the more theoretic you become, we don't always even know how to apply the 15th derivative of something, but we do it in that theoretical sense, and we want to have a better understanding. But the point is, we can take as many derivatives as we want. And, you know, again, if we go to a function like the square root of x, that's never going to peter out. So if I want to take the first derivative, I can. It's the 1/2 x to the negative 1/2. And then if we take the second derivative, we get negative 1/4 x to the negative 3/2. And then the third derivative, that exponent's just going to continue to shrink, really grow in the negative direction. We get negative, positive really, 3/8 x to the negative 5/2. And we can see that this is just going to continue to go all day long. So if we wanted to take the 151st derivative, we could do that. It would take a little bit of time. We might be able to come up with a pattern a little bit easier, probably a little bit faster to do that. But we can continue taking as many derivatives as we want, because all the derivative is a function. And so we can take the derivative of that function as many times. And there are some very, very visual, direct applications of this. This is not the only place. Position is not the only place. In economics, we use derivatives a lot to determine marginal cost and pricing, things like that. That's not the only application. So we have different places that we use these derivatives based on what situation we're trying to apply it to. The key is anytime we are looking at a rate of change, we want to know that instantaneous rate of change, we are looking for a derivative. And if we want to know how that rate of change changes, well, we're looking at another derivative, so we're going to continue taking derivatives.